Good morning. We are ready now. Moving on into chapter 18. So it's more thermodynamics. It's more looking at thermal energies of different types of gases and liquids and solids. Find out what the properties are. Chapter 18 officially is called Kinetic Theory of Gases. Now, the idea behind the kinetic theory of gases is actually what we already looked at in chapter 17. So there's a lot of overlap in these chapters. The kinetic theory says that what we call heat, or more specifically what we call thermal energy of a sample, is the kinetic energies of the molecules. So if I've got a collection of gas or liquid or solid molecules that make up that system, there's going to be some type of kinetic energy, either translation or rotation or vibration or a combination of all of those. And kinetic theory says that heat, or again more specifically thermal energy, is determined by adding together all of the kinetic energies of all of the molecules. So that's why I've added in and liquids and solids, and there's a nice picture of Yellowstone National Park here as a representation for that thermal energy. All right, so again, what we've got here is the units in chapter 18. I'm going to let you guys go through that. I just want to point out that we're going to take a look at a very quick example with mean-free path and diffusion, but that's not something you necessarily have to look at in a lot of detail. So I will be looking at examples of those. So let's take a look at this. We looked at the ideal gas law in chapter 17. We introduced that, so you guys are ideal gas law experts at this point, or by the time you've gone through the homework problems. And if we specifically start looking at gases as an example here, the assumption of the kinetic theory is that if we take any sample of any material, there's going to be a huge number of molecules and atoms that make up that sample. And in general, there's going to be some range of kinetic energies of those molecules. If I have a sample of gas molecules, some are going to be going faster, some are going to be going slower. So there's a range of kinetic energies. They don't all have the same kinetic energy. So they have a variety of speeds. But what we can do is we can determine what the average kinetic energy is. In fact, we can do more than that. We can it turns out that we can determine what the distribution of kinetic energies looks like. How many will be going more slowly? How many will be going faster? We can actually get a distribution of kinetic energies, a formula that tells us what that looks like. Now, for these gases, what we assume is that they bump into each other. There are collisions that take place. But when molecules come together, we're assuming that they hit and separate elastically. So if you think back to physics 4a, what we're saying is that when these two objects come together, they bounce off of each other, but there's no adhesion. There's no tendency for these molecules to stick to each other. The collisions are perfectly elastic. Kinetic energy then is conserved in these interactions. Okay, and that turns out to be not a perfect assumption for gas molecules, but it turns out to be a very useful assumption for most collections of gas molecules that we look at. The ideal gas law approach works really well. So we had written down the ideal gas law back in chapter 17, but now we're going to come back and actually look at a derivation. We can actually derive the gas laws and by taking a look at the different molecules. So what we've got here is we've got a volume that's set up, and we've got a collection of gas molecules, and we're showing that they're headed in different directions, kind of random kinetic energies, random velocities for the molecules. I guess I shouldn't be saying random, because what we're going to show is that there is a distribution that we're looking at. Now, if I take that cube, so we've got this set up as a cube right now, with each side having a distance of L, if I think of just one of those molecules, and I think of just one of those sides of the cube, what we've got is a gas molecule that bounces around inside this volume. Every once in a while, it hits this side and it bounces off. So if I just look at one of the sides, and I ask how much force am I going to get every time this molecule bounces and hits this side, if you remember back from Physics 4a, we can write the force as a difference in momentum, a momentum shift or a momentum change, divided by an interval of time. So during some interval of time, the molecule bouncing off that side is going to exert a force, and we can relate that to how much momentum changes during that collision. So if I have a molecule coming in, and I take a look at its momentum, you know, the only part of the momentum that's actually going to exert a force is the direction of momentum, or the direction of velocity, that is perpendicular to that side. So what we'll say is, if I'm looking at one of these sides over here, it's really just the x velocity. It's the x velocity that's going to determine how much force we're getting on that particular side. So the x momentum determines how much force on these two sides, the y momentum determines how much force on these two sides, and then the z velocity, how much momentum we have on the remaining two sides. So we're going to write that as a momentum shift, or a momentum, a delta momentum of 2mvx. So what happens is it comes in with momentum mvx, and since the collisions are elastic, it bounces off with momentum mvx. So that's 2 mvx's. Now, how frequently does that one molecule hit that side? And so the amount of time, again, if we think of the molecule as bouncing through, hitting this side, maybe hitting some other sides, and then returning to that same side, the time interval between collisions is going to be equal to the distance across the cube and back. Well, the distance from one side to the other is 2L. And then it's going to depend on how fast it's traveling. Now, for the sides we're looking at, it specifically has to do with the velocity in the x direction. And so if we look at the change in momentum and divide that through by the time interval between successive collisions, what we're going to end up with here is, on average, the force due to one molecule is going to be m times Vx squared divided by L. Okay, that's the force of one molecule on one particular side of the container. Now what we want to do is we want to look at the force due to all the molecules. Well, the way we would come up with the force due to all the molecules is we would add up a bunch of these terms. Now, all the molecules have the same mass. All the molecules are traveling the same distance, but the component of velocity in the x direction will vary. So what I would have to do is add together Vx squared plus Vx squared for molecule 2 plus Vx squared for molecule 3 plus Vx squared for molecule 4. I'd have to sum all of those together. What that says then is that the force due to all the molecules acting on just one side is m divided by L times the number of molecules times the average value of V squared. Now, the average value of v squared is, we're going to find out, this is something we call the root mean squared velocity. That's going to come from adding together all of the Vx squareds and then dividing through by the number of molecules. All right, let's look at this in a little more detail. So again, if we look at any individual molecule, it's going to have components of velocity, Vx, Vy, and Vz. Some of the molecules are going to be oriented so that most of their velocity is in the x. Some will be oriented in other directions. In any case, for each one of the molecules, we can say that v squared, their total velocity squared, is going to be the sum of Vx squared plus Vy squared plus Vz squared. Now that's just vector addition. So we're adding those numbers together. What we want to do now is find out what the average would be. So what's the average value of the velocity of the molecule? And that's going to come by taking the average of Vx, Vy, and Vz squared and adding all those individual averages together. Now by symmetry, the average value of Vx and Vy and Vz averaged over all the molecules in the system, those values are all going to be the same. And that says that any individual number of these, one of these averages, is going to be 1/3 of the total. So that 1/3 is coming into our formula as a result of the x, y, and z directions. So those directions combined tell us that instead of working in terms of just one component, we can replace that with the total value of v squared. So let's go back to where we were on that previous slide. We had said that each molecule exerts a force on this side, on one of the sides, mvx squared over L. Well, what we can do now is we can take out that Vx squared and replace it with 1/3 V squared. We don't need, I guess we do need the average there. So when we come in and replace that with the total force acting on this is going to be 1/3 times the number of molecules. This is our m over L that we had. And now we're going to replace that, instead of Vx squared, we're going to replace that with V squared. Now the V squared represents the, the combined velocity once we include all components together. And so that mv squared average, that can be written as the kinetic energy of that molecule. So we've now taken the velocities and rewritten those average velocities in terms of average kinetic energy. So we made a big deal back in chapter 17 about temperature and thermal energies are related to the kinetic energies of the molecules, and now we've made that connection. So the velocities have been rewritten in terms of kinetic energies, and now we can take what we call the force acting on one of the sides, and we want to change that into pressure. So rather than the force acting on one side, we can rewrite that in terms of the pressure that exists throughout the entire sample. So the pressure doesn't just exist on one of the sides. We're going to calculate it that way. Once we find out what the pressure is, that value of pressure exists throughout the sample. So that's something that exists at every location throughout the sample. Now to get the pressure acting on one of those sides, force over area, the area of that side is L squared. We already have one factor of L in our formula for force. When we add that additional factor of L squared, that gives us L cubed, and L cubed is the volume of the container. So now we've got the pressure is equal to N over V. There's a 1/3 out here. If you remember, the 1/3 came in from combining Vx, Vy, and Vz together. And that can be written in terms of the average kinetic energy. Flipping some of this stuff around, bringing the 2 outside, really, is saying that the pressure then, the pressure of that sample of gas molecules, the pressure depends on how many gas molecules there are per volume, right? So if I have more gas molecules packed into this volume, that's going to give me more pressure. And it's also, pressure is directly proportional to the average kinetic energy of those molecules. So that kind of makes sense. If I have more molecules, that's going to increase the pressure. And if those molecules on average have more kinetic energy, that's also going to increase the pressure. So that's getting the pressure of a sample of molecules in terms of the individual properties of the molecules that are contained. Now I can start from that formula and then make a connection with this. What we can do is take the formula we've derived, write the PV on one side, and then say that what we're left on the other side is 2/3 NK average. Well, that looks a lot like the ideal gas law. So this is actually the way temperature is defined. This definition of temperature is related to the kinetic energies. Now, of course, temperature predates the concept of kinetic energy. Go back hundreds and hundreds and hundreds of years, people had temperature, was something that people understood could be measured. But with this addition, now we can show that this temperature, which the definition goes back hundreds or possibly thousands of years, can now be written in terms of kinetic energy. So now we know what temperature is, and we can define temperature in a way where temperature and kinetic energy are directly proportional to each other. All right, by taking an observation of, this is our definitional formula for temperature, and seeing how this is related to kinetic energy, that allows us to set temperature, write down a formula showing how temperature specifically is related to kinetic energy. And what we find is that the kinetic energy, by this definition, is 3/2 Boltzmann's constant times the temperature. So whatever the temperature is, this is now telling us how much kinetic energy, on average, those gas molecules will have. Now, it's a particular type of kinetic energy that we're talking about here. Remember, we talked about kinetic energy of molecules could be translational, it could be rotational, it could be vibrational. Now, the formula we have so far is in terms of translational only. So it's saying the translational kinetic energy, on average, is 3/2 Boltzmann's constant times the temperature. So we've been saying temperature and kinetic energies are proportional, and now we know what the proportionality expression is that relates those two. Okay, this is kind of a big deal, I know. I mean, physicists get kind of carried away with all these things, but that's kind of fascinating to think that, well, that's the relationship between temperature and translational kinetic energies. All right, and then here's this is kind of the same stuff we saw in the previous one. This is a continuation of that, of the textbook's derivation. And it's kind of the same thing. I'm just going to move on from here. You can take a look at that. That will be in the slides. And then they have, yeah, the same thing we just talked about, showing that the average kinetic energy of a molecule is the average value of 1/2 mv squared. And that now we can show is 3/2 little kt, where T is this thing we've defined as temperature. So I put this yellow box around this. This is a big deal. Average translational kinetic energy directly proportional to temperature. Okay, so let's try doing some calculations here. This first example says, okay, well then if I have some kind of a collection of gas molecules, and we're assuming that they behave the way we've set up in our ideal model is, the gas molecules are bouncing around and they collide, but they don't stick to each other, then we should be able to use the formulas we just derived to find out, hey, at a particular temperature, how much energy do the gas molecules have on average? And this is what those calculations would look like. So on average, the translational kinetic energy is given by 3/2 little kt, where little k is Boltzmann's constant. So here's Boltzmann's constant here. Now, remember, we can't use Celsius. Celsius is not an authentic temperature scale. We need to use an absolute temperature scale. So we're going to switch from 37 Celsius over to 310 kelvins. So we're going to switch over into kelvins. Now there's a lot of K's in these formulas, so let's be really clear. Big K is being used for kinetic energy. Big K is also being used as a unit for kelvins. So you don't want to get those mixed up. I mean, the big K kelvins is a unit. The big K kinetic energy is a variable. So hopefully that works. And then the other little k going on here is Boltzmann's constant. So these are definitely case-sensitive formulas. You got to know the little k's from the big K's, and then you got to know that the big K's are being used for units. In other situations, they're being used for kinetic energy. All right, so done. I mean, this is such a simple formula. Once you put in the temperature in kelvins, multiplied by Boltzmann's constant, 3/2, the average kinetic energy of any gas molecule, doesn't matter what species, oxygen, nitrogen, hydrogen, helium, is going to have a translational kinetic energy on average of 6.42 10 to the minus 21 joules. Okay. Now, this 10 to the minus 21 here, joules, that's telling us that we're looking at just one molecule. That's reminding us that it's such a tiny, tiny, tiny amount of energy. It's not a collection of molecules. It's just the one molecule. And, I wrote this down. Helium, neon, argon, nitrogen, oxygen, carbon monoxide, carbon dioxide, methane, whatever gas molecules you're thinking of, that's how much translational kinetic energy they're going to have. Now, I extended the problem a little bit, so there were some more things that I was a little curious about and wanted to see some numbers on. I said, okay, fine. What if we take a 1 cubic meter sample of these molecules where there's a pressure of 1 atmosphere? So, how much internal energy would there be? Now, internal energy is this. Internal energy is not the energy of one molecule. The internal energy comes from adding together all of the energies of all the molecules in our sample. So that says that the internal translational kinetic energy for the entire collection would come from taking the number of molecules and multiplying it by this average value. So that would say that the total translational kinetic energy of the entire molecules in this sample, this 1 cubic meter sample, would be 3/2 nkt. Now, the ideal gas law tells us that for a collection of gas molecules, n little kt could be calculated as P times V. So rather than counting the number of molecules, what we could do is just measure the pressure and the volume. Either of these will tell us how much energy there is in my molecule. So let's do this. Let's say that we could use air. So let's say that I've got all these air molecules in the room right now. Ooh, 37 Celsius, that's kind of warm. So that's on a really warm day, somewhere in the 90s, probably 99 Fahrenheit, something like that. What we can do is go in and calculate by using the pressure and the volume and the temperature numbers, it says that that 1 cubic meter would contain 2.34 10 to the 25th molecules. So that would be the total number of molecules in that sample. Now, to calculate the total internal energy, well, the internal energy of the sample, what we can do is take those number of molecules, multiply it by the average. Ooh, that needs a joule on it, add that in. Sorry about leaving that out. And what I ended up with was 150,000 joules. So that says, you know, if I took 1 cubic meter of air, how much translational kinetic energy do all the molecules have? That's it, 150,000 joules. That's the total translational kinetic energy of our entire sample. So the important thing we want to take away from this is this K bar is the average kinetic energy, and then by taking this average value, multiplying by the total number of molecules, we can get what we call the internal energy of the entire sample. Okay, that's the important item. All right, another item that this is going to allow us to calculate then is, since this is based on kind of an average speed, what we can do then is we can take this kinetic energy and we can convert that back into a velocity. Now let me go back one step on this, and let me go back 2 steps on this. Let's go back to here. What we've got from here is the kinetic energy 1/2 mv squared. Kinetic energy on average depends on the average value of velocity squared, is set equal to 3/2 kT. We can take this part of the equation and solve for an average velocity. Now, the formulas we have, kinetic energy actually depends on velocity squared. So we don't quite have the average value of velocity here. What we have is the average value of velocity squared. Well, that doesn't have units of velocity. What we could do is we could take a square root to get the units back into a velocity. Now what we call this is the root mean square of the velocity. So what this is, root mean square, actually says, first of all, you take every velocity of each molecule. For each one of the velocities, you square it. That's what the square is. And then, once you've squared all of them, you take the average value of those squared values. So we're not taking the average of the velocities themselves, we're taking the average of the squared values of the velocity. And then once we've taken all the squares, and we've taken their average, which is what mean is, then we take a square root of that value to put it back into standard units of velocity. And so, and then we call it RMS. So VRMS, kind of this average value of the squared, square rooted, is given by 3 kT over m. So it says, hey, if I've got a bunch of gas molecules, I can figure out, kind of on average, how fast are they traveling. Okay, so here's our first example. It's saying oxygen, nitrogen molecules at 20 Celsius. How fast are they traveling? So the formula that we just derived says the VRMS is given by 3 kT over m, where, let's be really clear about that, little k is Boltzmann's constant, and little m is the mass of one molecule. Now, this formula looks simple enough, but I'll tell you right now, on midterms and final exams, this has a very high failure rate. And that's because there's a couple things you have to keep track of. The first thing to keep track of is that the little m in this formula is not the mass of the sample. It's not the mass of all the molecules. It's the mass of one molecule, and I know that because it's paired up with Boltzmann's constant. Boltzmann's constant is keeping track of the properties of individual molecules. Now, rather than work in terms of Boltzmann's constant and the mass of one molecule, it's easier to scale this up. If I scale this up so that I'm working in terms of an entire mole, then I can take the mass and replace that with the molar mass. And that's the first step I am going to suggest in order to make the success rate of these calculations higher. So, for oxygen, for example, the molar mass here is 32 grams per mole. Now, the second item that we have to be careful with is molar masses are given in grams, but grams aren't standard units for us. For us, the standard units of mass are going to be kilograms. And so for O2, I need to write that as 0.032 kilograms per mole. So let's check real quickly. Off the periodic table tells me the molar mass for nitrogen is 14. The molar mass for oxygen is 16. Since oxygen and nitrogen exist in our atmosphere as diatomic molecules, I have to double the 16 for oxygen to 32, and I have to double the 14 of nitrogen to 28. And then I have to convert those into kilograms, not grams. And so that's why I need to use 0.032 for oxygen, 0.028 for nitrogen. Now once I do that, then I just have to make sure that I'm using an absolute temperature. So that 20 Celsius, that's not going to work. I've got to convert that into kelvins. That's going to become 293 kelvins. And then for the gas constant, I'm going to use 8.314. So I carried this out for oxygen, carried it out for nitrogen. What I found was that the VRMS speed, which gives us kind of an average, for an oxygen molecule in the air is 478 meters per second. And I want to say that's really fast. So these air molecules are moving, that's approaching the speed of sound here. These are some pretty fast moving molecules that we have here, faster than the speed of sound. 478 meters per second. And the nitrogens are going even faster. They're going at 511. Now, why is it that the nitrogen are going faster than the oxygen? Well, let's think about this. What we've been saying is that every molecule, on average, is handed the same amount of kinetic energy. So it's the kinetic energy that gets divided up kind of equally. On average, every molecule gets the same amount of kinetic energy. Well, if on average I'm giving all the oxygens the same amount of kinetic energy as I am nitrogen, when we look at their speeds on average, the lighter molecules are going faster. So again, it's kinetic energy that gets kind of divided up so that all of the different molecular species have the same distribution of kinetic energy. On average, they'll get the same amount of energy, and that means that the heavier molecules are going slower. The lighter molecules, on average, are going faster. And that's what accounts for this difference in the molecular speeds that we have set up here. And then down here at the bottom, just to emphasize this, it's saying, hey, the average translational kinetic energy is the same for both of them. Both of the oxygen molecules and the nitrogen molecules, on average, at 20 Celsius. 6.07, 10 to the minus 21 joules, but the speeds are going to be different. Okay. So again, this is an RMS speed difference. Let's see. Here's a conceptual example. It says that we have a tank of helium. We're filling balloons with that tank. Each time the balloon is filled, the number of helium atoms remaining in the tank goes down. How does this affect the speed of the molecules? And you know what? The speed of the molecules just depends on the temperature. So if this tank of helium is in the room and it's being kept at the same temperature because of thermal contact with its environment, the molecules are going to be traveling at the same speed, right? As long as the temperature stays the same, the molecules will have the same distribution of speeds. Now, let's see what one of these VRMS calculations might look like, just as a way of experiencing what VRMS really means. Let's say that we have 8 molecules, and they have speeds of 1, 6, 4, 2, 6, 3, 2, 5. Those are really low speeds, but that's to keep the calculation easy. So what they're asking us to do is calculate the average speed and then calculate the RMS averaging. So let's do that. And you guys have been doing averaging since 3rd grade, right? So you know that to get an average value, you add up all the values of the individual molecules, in this case, 1, 6. Well, if I add all those numbers together, I get 29. There are 8 molecules, so here's the formula for averaging. Now I've used the summation sign here, but it really comes down to adding all those values together and dividing by 8. The average value is 3.63. And it looks like some of my periods, well, this one in particular, looks like a comma. I apologize. That's a period. That's a decimal. 3.63 meters per second is the average or the mean value of the velocity. How does the RMS value differ from the mean? And for the RMS value, instead of just taking the velocities and adding them all together, we first of all square each one. So 1 becomes 1, 6 becomes 36, 4 becomes 16, and you know, that's the pattern here. So what I've done now is instead of adding all the v's, I've added all the v squared values. Now once I add all the v squared values together, I divide through by 8. So to carry out an RMS calculation, I added up all the v squared values divided by 8, and that gives me 16.4, but wait a minute, the units here would be meters squared per second squared, because what we've done is we've taken all the v squareds. Now, in order to get back to a standard velocity, I need to take a square root. And so that square root brings me back to 4.07. So just the plain straight average mean value of velocity, 3.63. When I do the RMS averaging, I get 4.07. Now, what's happening here is it's a different sort of averaging. And the reason we do the RMS value is so that the RMS is directly related to kinetic energy. Kinetic energies depend on v squared, not on v. And so average kinetic energies are related to average values of velocity squared. That's the reason we're doing this as an RMS. Ooh, there's a cross out here, which I needed to leave out. I didn't. I'll get that edited out maybe. In any case, not a big deal. But the average translational kinetic energy is 1/2 m VRMS squared. So now I can write those average kinetic energies directly in terms of VRMS. Now, since we're averaging the v squareds, the VRMS values are always going to be larger by a certain amount. So in this case, we can see it's larger, 4.07 than the 3.63. Not such a big deal, but you know, just a reminder that RMS is not the same thing as doing a straight average. All right, here are the formulas for distributions of these molecular speeds, and this is a good example of looking at distribution formulas. Now, I'm guessing in Calculus 3B, I believe it is, there is a chapter in Math 3B or they go through probability distribution functions, PDFs. And that's very much what we're looking at here with molecular speed. So first of all, let's just go ahead and write down the formula. It turns out that when we have a collection of gas molecules, that our understanding is that some are going faster, some are going slower, there's kind of an average value. But we can also go in and say very specifically how the gas molecules are arranged in terms of velocity, and that seems kind of remarkable. It's not like just any pattern of velocities are what we observe. We always observe this particular pattern. And what it says is, not as many molecules going slower and not as many molecules going faster. Most of the molecules are in kind of an average range. Now, within this average range, there is a most likely speed at which they're traveling. There is an average speed, a mean, and then there's an RMS. And those three velocities are always in the order that this graph is showing. So the most probable value of velocity is a little less than the mean value, which is a little more, and then the RMS value is a little larger from each of those. What we have on the horizontal axis here, there's our velocity, or the speed of the molecules, and then along the vertical axis is this function. Now this function is telling us how many molecules there are for a given speed. So it says at really low values of V, there aren't very many molecules, and then as I go to higher velocities, there are more and more molecules with these higher velocities, but then when I go to extreme velocities, the number drops off again. Now, why would that be? And it's all just statistics. So the distributions of molecular kinetic energies and the distributions that we see of velocities, it has a statistical basis to it, and we're going to go through that. So, when I first look at this formula looks just a bit terrifying. But let's actually go through and kind of break this down into different pieces. So it turns out that the formula that we have, let me go back and take a look at that formula and point to a couple things first. I'm going to take this formula, I'm going to break it into three separate factors. So the first factor I want to look at is actually the last one here. Let me cover up this period. There's a factor right here, this exponential factor. And what I'm noticing is that is 1/2 mv squared divided by kT. You know what 1/2 mv squared is? That's the kinetic energy of an individual molecule. So what this factor is telling me is as we go to higher and higher kinetic energies, they become less and less probable. Why would that be? Well, it turns out this comes from doing a maximization calculation inside a branch of physics called statistical mechanics. And what we can show is that if I have a collection of molecules, there's not an infinite amount of energy available to those molecules. At a given temperature, there's a certain amount of energy that's going to be available to those molecules. And so what happens is lower amounts of kinetic energy are more likely. As we go to higher and higher amounts of kinetic energy, it just becomes less and less probable that any individual molecule would end up with that amount of energy. So this is our energy limitation factor here at the end. We also have a factor of 4 pi times v squared, and we'll see in the next slide what that's coming. But 4 pi v squared, maybe it reminds you of the formula for the surface area of a sphere. And that actually is related to velocity and the ways. Well, I guess this is the question we have to ask. Are there more ways to go fast or more ways to go slow? and or are there equal number of ways of going fast and slow? Turns out there's more ways of going fast, and we'll look and see why. And then finally, all these other factors here are only here in order to make sure that this probability distribution normalizes out to the right number of molecules. You'll see that there's a factor here of the number of molecules. Everything else has to normalize to a probability of 1. All right, so here is our diagram explaining why there are more ways to have high velocity compared with low velocity. So what we want to do is this. We're going to draw a three-dimensional diagram here that has Vx, Vy, and Vz on it. I guess that's a right-hand coordinate system. That's a three-dimensional picture. I did my best. So here is Vx, Vy, and Vz. Now, what quantum mechanics tells us is that each combination of Vx and Vy and Vz are equally probable. They actually correspond to a quantum state. So each value of Vx, Vy, and Vz that we can come up with is a particular quantum state. And that says that if I now take spherical surfaces, so now I'm thinking of a spherical surface. If I pick any point on that spherical surface, it has the same velocity. Now it has different individual components of Vx, Vy, and Vz, but the total velocity is the same. And since kinetic energies are going to depend on total velocity, kinetic energies don't depend on individual components, that says that any combination of velocities that places us on that spherical surface has the same amount of kinetic energy. So that particular shell, spherical shell, all corresponds to a given kinetic energy. If I move farther out to a bigger sphere, all the points on that correspond to a differing amount of kinetic energy. This bigger sphere corresponds to molecules with more kinetic energy than this one does, So what's happening here is as you move out towards more and more kinetic energy, there are more possible quantum states. There are more ways to go fast than there are to go slow. There's only one way to be at rest, right? And that's a point right at the center. So what happens in this formula then, when we're trying to decide how these velocities are distributed, is that if I'm just thinking in terms of how many quantum states are available, that's going to increase like a spherical shell. So a spherical shell has a surface area of 4 pi v squared, and then it has a thickness of dv. The energy factor that we already talked about says that as energy goes up, it becomes less and less likely any individual molecule will have that much kinetic energy, and it specifically drops off like an exponential factor. When we combine both of those effects together, what we end up with is the formula that we were looking at, where at first we see more and more molecules as we increase velocity, and that is that's the more ways to go fast than go slow effect. Now, for a while that dominates, but as we go to higher energies, it becomes less and less likely that a molecule would end up with that much energy. And so statistically, what happens is the distribution drops off. Now, if we take any collection of gas molecules, any large collection of molecules, it follows this distribution really, really well. So we feel like we have a good understanding of this in terms of the possible quantum states, and then statistically, we run statistics on this and ask what's the most likely way the energy would be divided up. And it gives us this particular function. When we go into the lab and measure the velocities of molecules in a sample, they follow this distribution, extraordinarily well. So it works, right? This is an example where our derivations work really well. Now in this example, they're asking us to go in and come up with formulas for the average velocity and the most probable velocity. And so we're going to do that. So again, going back to this distribution, or actually going back, here we go. Going back to this, that's the formula that we want to use. That's been derived for the distribution of speeds. And then there's a most probable value. Now how would I get the most probable value? And the most probable value would come from taking this function, taking a derivative with respect to velocity, setting that derivative equal to 0, and finding out what value of v that corresponds to. That should be a familiar sort of calculation from your calculus classes. And then also, maybe in Physics 4a, a few of those examples came up. But definitely you guys are kind of calculus experts. So that should make good sense that we're trying to find out where the function peaks at what value of velocity. Now for average velocity and average velocity squared, what we would do is we would, and again this is something I think you've seen in Math 3b, you would take our probability density function, slip a factor of v in there, or a factor of v squared, and carry out the calculation. So let's see what that would look like. So in physics, these kind of calculations they're a big deal, and in engineering, and in the sciences in general. So here's the function overall. Now what I've done is, onto this function I have added a factor of dv. Okay, so the factor of dv has been added in, and then here was our energy limit expression. Here is the number of quantum states expression with the dv added in. And then here is the normalization factor. And then here is the number of molecules. Now what should happen, the way normalization works, is if I take this function and divide it up into a bunch of vertical columns, each one of these areas corresponds to the number of molecules that fall within a certain velocity range. Right? That's how we carry out integrations. So the number of molecules in here is given by my probability distribution function times dv. dv is the width, and then function of v is the height. And in the limit, where these are really, really narrow, I can treat those as a series of rectangles. So this should be just standard stuff that you have seen in your calculus classes, and some of it you've seen in Physics 4a, like integrating the energy of a spring, an ideal spring, something like that. All right, so the way this function works then is that dn is equal to a function of v, dv. Another way to write that is that this function that we've come up with is the number of molecules divided by the width of the velocity bins that we've set up. Now if I integrate across all of those bins, that's the same thing as integrating that function across dv. That should give me the total number of molecules, right? If I add up all the molecules in all the possible bins, that's going to give me the total number of molecules. Let's see if that works. That should work. So here we are, we're integrating over all of these, and I've factored out a bunch of constants. Now, the velocities need to stay inside the integration sign, and the kinetic energies also depend on velocities. They need to stay inside the integration sign too. Now, when we carry out these integrations with these exponentials, a common trick that we use in physics all the time is to take the argument of the exponentials and define that in terms of a unitless variable. So in physics and in engineering, what we know is that anything that's in the argument of an exponential, it can't have any net units. So kinetic energy has units of joules. Well, kT also has units of joules, and the units cancel out. So what we'll do is we'll take kinetic energy divided by kT. I'm going to use x, where x is a unitless variable. It's proportional to the energy, but the combination itself has no units. Same thing as 1/2 mv squared over kT. So we're going to change the variable to carry out the integration. That's got some nice features to it when we carry this out. So if I now write down my variable substitution I'm going to use, what we're going to say then is that since x is equal to 1/2 mv squared over kT, v squared is the same thing as 2kt over m times x, and v by itself is going to be the square root of that, and then dv also has to get substituted, and dv I get by taking the integration, or the derivative of this expression. So the constants remain the same, but when I take a derivative of x to the 1/2, I'm going to get 1/2 x to the minus 1/2 dx. So here are the variable substitutions, and then, one by one we can substitute out the velocities and substitute in the factors of x. Now when I do that, this integration that we set up, now all the constants are still here, but when I look inside the integration sign, I now have e to the minus x. And when I get over to the factors of v now have factors of v have been replaced with factors of x. And also very important, the dv has been replaced with dx. Now we can carry out this integration. I'm not going to go into the details of carrying this out. This integration, to me, to most people that do physics, once you've seen this integration a few times, you realize you can just look it up in a table. This actually becomes the factorial. This integration right here is the factorial of whatever this power is. It's a 1/2 factorial. You can also carry out the integration using integration by parts and then using some other tricks. Anyway, I carried out the integration. Everything canceled out except for n. So what that tells us is we seem to have the right set of normalization constants. All of the constants in that function, when we carry out the integration, everything cancels out, so that integrating this over all possible values of v, and all the possible values of v run from 0 to infinity. Right, so the limits on my integration, 0 to infinity. Once I allow for all possible values of velocities and carry out the integration, it says this integration gives me the total number of molecules, which it was supposed to do. So we can check that off. That says that, yes, the function does have that correct property. All right, let's see if we can do some more with this. We want to go in and get the average value of velocity. Now, the way we take a probability function, like f sub v, and calculate an average value of some variable, is to take the very same interval we had before, but now we're going to multiply it by v. That's going to give us the average value of the velocity. Now, just looking ahead, when we do the RMS value, instead of getting the average value of v, we want to get the average value of v squared. So we're going to put a factor of v squared in there. So those are both examples of calculating average values of something by putting that extra factor into a probability distribution. So with this, what I did was I put that extra factor of v in. Now when I put the extra factor of v in, what that led to was an extra factor of 2kt over m to the half, and it led to an extra factor of x to the half. So if you go back and compare this with the previous integration, I've got extra factors here and here. Now the integration itself works out very similar to what we did before, except as mentioned, I've got this extra factor of 2kt over m to the half, and I've got an extra factor of x to the half here. When I carry out this integration, this right here turns out to be 1. And so combining all of this together gives me 8 over pi to the half times kt over m to the 1/2. That actually is the formula for the average, just the straight average or mean of the molecular speeds. So the molecular speeds are going to depend on temperature, and they're going to depend on mass. Now, with the RMS value, we already solved the RMS value using the ideal gas law derivation. So that we already have solved using a different technique. What we can do now is take this distribution and find out, does it agree? Two different ways of calculating VRMS. Are they going to give us the same value? I hope so. If not, then we have to go find out where the inconsistencies are. If we take this particular function, plug that into the formulas here, what that says is, since this is now v squared, we're going to pick up, once again, extra factors of m over 2 pi kt. So these, we're going to have extra factors in here. Yeah, so we've got an extra factor of v going on. We're going to pick up extra factors of 2 kt over m. And we're going to pick up an extra factor. This was x to the 3/2. This is now x squared, or x to the 4/2. So again, if you go back to the previous slide, you can see how the factors of x are increasing, and these factors of 2kt over m are also increasing. These are left over from the original formula, so I shouldn't have been referring to those. But these are steadily increasing. When we carry out this integration, what we end up with is x to the 3/2, and we end up with a full factor of 2kt over m here. So I carried out those integrations. I looked up, or used a formula for 3/2 factorial, and then started canceling terms. And the average value that we got for v squared, which should be, we're hoping, is VRMS, and it is VRMS squared, is given by 3kt over m. Now remember, this is squared at this point, so we got to do a square root on both sides. And so carrying out this detailed integration suggests that VRMS should be 3kt over m to the 1/2. Well, that's good news, right? That agrees with the calculation we had done before. So two different techniques for going in and calculating VRMS, they both provide the same result. So that's, I'm going to claim that's good news. That fits in with what we had looked at before. So in summary, now I know what happens with these integrations is this. Usually what happens is when we start doing some of these integrations, students get really excited because they go, oh, now I can use some calculus. Here's a chance to use what I've been learning in my calculus class right here in physics. We can actually try and gain a better understanding of these gas molecules and their speeds by using calculus. Now I know there's a lot of detail to this. It's not something you guys have to reproduce on a midterm. So let me say that up front. I'm not expecting you guys to carry out a derivation of this on the midterms. On the other hand, if you understand how this all comes together, it's going to reinforce your understanding of calculus, it's going to reinforce your understanding of physics, and just in general, you'll be better at problem solving. but I do understand this is a little more detail, and that I know, looking around at the class here, there are going to be students that embrace this and go, this is such a cool example, and others that think, oh my gosh, this is a little beyond what I'm used to in my calculus class. Either way, I think there's places to learn things and pick things up from this. So, one more thing we have to do here. The last item was what's the most probable velocity, and that says take this function, take a derivative, and then set that derivative equal to 0 and solve for the value of velocity that corresponds to. Now, often when you're doing maximization of functions, where you're trying to find out how, where does the function maximize, a lot of times you don't have to do the whole function. So for example, in this case, I've got all these constants out front. I don't have to keep these around. That won't change the results. So I can ignore all the constants out front. What I can do is I can just focus on whatever has a factor of v. As long as I keep all the factors of v, I can take a derivative of that. That'll work just fine. So that's what I've done here. I can take this function and I can maximize that. So I took a derivative with respect to v. Now, I want to use the product rule here. So I've got a factor of v squared. Then I have this exponential, which is also a function of v. And so, the derivative of v squared times this portion over here, plus the derivative of this portion times v squared. And so I wrote all that out. And then I set the whole thing equal to 0, factored out, canceled out some common factors. And what I ended up with was the most probable velocity squared is 2kt over m. So let's take one more look. In fact, I think we're getting pretty close to the end of today's class. So let me just summarize what we've done here, because this was a lot. Here is our function, our distribution of molecular speeds. And what we said was there's kind of 3 different sorts of averaging that we might do here. One of those is referred to as the mode. So think back to your math classes when you were covering statistics. The mode was the most likely individual outcome. And so the mode here is the most probable velocity. Now the mean is the average value that comes from adding all the possible values together and dividing through. The RMS comes from combining all the v squared values and averaging those. And what we find is, what we claimed from the graph when we looked at it before, is that the mean is a little bit beyond the peak. The tail on this side is bigger than the tail on the other side of this function. And so the average value is a little bit higher, and the VRMS will be a little bit higher than that. So that's what we're expecting we'll see in these formulas. And sure enough, when we go through and write these 3 formulas that we've derived, the mode, the most likely value, is kt over m to the half times the square root of 2. The mean is kt over m to the half times the square root of 8 over pi. Now if you take the square root of 8 over, or if you take 8 over pi is about 2.5. So this is like square root of 2, this is like the square root of 2.5, and then the RMS value is proportional to the square root of 3. So that's how they're related. 2 to 8 over the square root of 2 to the square root of 8 over half to the square root of 3. Now, just to throw some numbers in and play around with these formulas, I put in some values for nitrogen at a temperature of 293 kelvins at room temperature. And if you remember, we did this problem once before for VRMS. We got 511 meters per second. Well, going in and calculating this for the most probable, I got 417. So that's fairly different, right? The most probable speed of one of these nitrogen molecules in the air is 417 meters per second. Now, if I look at the overall average, that's 471, and then if I look at the RMS value, it's 511. I like that calculation. I like thinking in terms of air molecules, because air is something that I experience all day long, every day. And a temperature of 20 seems pretty familiar to me, and that's an example of what these three different types of averaging tell me about the speeds of molecules in the air. If I redid this with oxygen, it wouldn't be very different. It would be pretty similar. So that's a good place. I think we're past time for the day. So we'll wrap it up right there. That's kind of the first half of chapter 18. We'll come back with our next class and take a look at the rest of chapter 18.